Our understanding of the universe, from the smallest particles to the largest galaxies, relies on the framework of physics. For centuries, physicists have sought to define the fundamental building blocks of reality. Traditional particle physics, the prevailing model for decades, identifies these building blocks as point-like particles. These particles, such as electrons and quarks, are imagined as infinitesimally small, zero-dimensional points in space. String theory, however, offers a radical departure from this view. It proposes that the universe's fundamental constituents are not point-like particles, but rather tiny, one-dimensional objects called strings. These strings are incredibly small, far smaller than anything detectable by current technology. Imagine a single atom. Now imagine something billions of times smaller than that. That's the scale of strings. String theory suggests that these minuscule strings vibrate, much like the strings on a violin. Just as a violin string produces different notes depending on its vibration, different vibrations of these fundamental strings give rise to the different particles we observe. In essence, the universe, in all its complexity, might be the symphony of these vibrating strings. The implications of string theory extend far beyond redefining the fundamental building blocks of the universe. One profound implication is the existence of extra dimensions. We experience the world in 3 spatial dimensions, but string theory requires 6 additional ones. These extra dimensions are thought to be curled up within the fabric of space-time. String theory suggests our universe has extra dimensions curled up at a small scale. Gravity is intimately connected to these extra dimensions. String theory offers a way to unify gravity with other fundamental forces. String theory's exploration of extra dimensions leads to a mind-boggling possibility: the existence of parallel universes. These universes would not be distant realms, but could exist right alongside our own, separated by the infinitesimal distances of the curled-up dimensions. Imagine 2 sheets of paper held parallel to each other. They represent 2 different 3-dimensional spaces. Now imagine a tiny string stretching between them, its ends anchored in each sheet. This string would exist in both spaces simultaneously, connecting them in a way we can barely fathom. These parallel universes are not just a product of science fiction, but a natural consequence of string theory's mathematical framework. While the idea is still highly speculative, it raises profound questions about the nature of reality and our place within the grand cosmic scheme. Section 4. Harmony and discord string theories, promise and problems. String theory, with its elegant framework and potential to unify physics, holds immense promise. It offers a glimpse into a universe far stranger and more interconnected than we ever imagined. However, the theory is not without its challenges and criticisms. One of the main criticisms is that string theory is incredibly difficult to test experimentally. The strings are so small that directly observing them with current technology is impossible. This lack of experimental verification has led some to question whether string theory is truly science or more of a philosophical exercise. Another challenge is the sheer mathematical complexity of string theory. It requires sophisticated mathematical tools and concepts that are still being developed. This complexity makes it difficult for even seasoned physicists to fully grasp the theory's intricacies. A universe yet to be unraveled. String theory remains one of the most active and exciting areas of research in theoretical physics. It's about pushing the boundaries of human knowledge. Whether string theory proves correct or not, it has profoundly impacted our understanding of the universe. The journey to unravel the universe's secrets continues.